Hello, in this lecture we answer two questions. In the first question we find out of this green shape, and in the second question we find out of this square ABCD using three different methods. Let's start with the first question. In the drawing we have a circle that is inscribed by this triangle ABC. You know that side AB of triangle ABC equals to 6 units in its length, side AC equals to 7 units in its length, side BC equals to 9 units in its length, side BC equals to 9 units in its length, and our task is to find out of this green shape. So first of all, we will define angle ACB. This angle is theta. That is to say, angle ACB equals to theta degrees in its size. So here we can implement the law of cosines. Repeat quickly on the law of cosines. So we need to, first of all, the law of cosines is true in any triangle. This is triangle ABC, that could be any triangle. Side AB of triangle ABC equals to A units in its length, side AC equals to B units in its length, side BC equals to C units in its length. This is angle BAC. Is equals to theta degrees in its size. This triangle ABC, the following equation is true, that cosine theta equals to A square plus B square minus C square over 2 times A times B. Again, cosine theta equals to A square plus B square minus C square over 2 times A times B. So I can implement the law of cosines in our triangle ABC. According to the law of cosines, this triangle ABC, cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 9. And again, according to the law of cosines, this is triangle ABC, cosine theta equals to 7 square plus 9 square minus 6 square or 2 times 7 times 9. Seven square is 49, plus 9 square is 81, minus 6 square is 36, divided by 7 times 9 is 36, and 36 times 2 is 226. 49 plus 81 is 130. 130 minus 36 is 96. So note that cosine theta equals to 9. Again, 130 minus 36 is 96 over 126. So in total, we found out that cosine theta equals to 96 over 126. Over 126 is 0.7169. So if you know that cosine theta equals to 0.7169. We would like to find out the value of theta itself. In order to find out the value of angle theta itself, we'll operate the opposite function for cosine, that is r cosine, on the result of cosine theta, that is 0.7169. In this way, we find out the value of angle theta itself. So r cosine, that is the opposite function of cosine, of 0.7169 is equal to angle theta, and r cosine 0.716 is equal to 40.368 degrees. We found out that angle theta equals to 40.368 degrees in its size, and therefore 180 degrees minus theta is equal to 180 degrees minus 40 degrees minus 40.368 degrees is actually equal to 139.362 degrees. It again, in total, we found out that 180 degrees minus theta equals to 139.362 degrees. So here we will find out the area of this triangle ABC according to a special formula. The area of triangle ABC is equal to the square root of S times S minus A times S minus B times S minus C. And again, this triangle ABC is equal to the square root of S times S minus A times S minus B times S minus C. A, B, and C are the side lengths of triangle ABC that are 6, 9, and 7, and S is the semi-perimeter of this triangle ABC. What is the semi-perimeter? The semi-perimeter is the perimeter over 2. That is to say, it is equals to the perimeter that is 6 plus 7 plus 9 divided by 2. So the semi-perimeter of triangle ABC, S is the abbreviation for semi-perimeter. S equals to 6 plus 7 plus 9 That is the perimeter of triangle ABC divided by 2. 6 plus 7 is 13, and 13 plus 9 is 22. So 22 over 2 is 11. So the sum perimeter of this triangle ABC is equal to 11 units in its length. So A equals to 6, B equals to 7, and C equals to 9. So there is equals to the square root of S times S minus A times S minus B times S minus C. So that after ABC is equal to S, the square root of S. S is 11, and S minus A is 11 minus 6, that is 5, times S minus B. S is 11, so S minus B is 11 minus 7, that is 4, times S minus C. S is 11, C is 9, so 11 minus 9 is 2. So in total we found out that the outer ABC is equal to the square root of 11 times 5 times 4 times 2. The square root of 4 is 2, so we take 4 out of this root. The square root of 4 is 2, so it is 2. Inside the root we left only with 11 times 5 times 2. So the outer ABC in total is equal to 2 times the square root of 11 times 5 is 55, and 55 times 2 is 110. So in total we found out that the outer ABC of this ABC it is equal to 2 times square root of 110 students in size. And the semi-perimeter of the triangle ABC is equal to 11 units in its length. In the next step, we define the center of this circle. This point is point O. We define the point of tendency of tangent BC with this circle. This point is point S. We define the point of tendency of tangent AC with this circle. This point is point Q. And we define the point of tendency of tangent AB with this circle. This point is point L. In the next step, we join points O and S together by a straight line. Point S is the point of tendency of tangent BC with this circle. So point O is the center of the circle. Point S is the point on the circle itself. Therefore, OS is the radius of the circle that we define as R. The radius OS is equals to R. The radius OS is drawn to point S, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius BO. Tangent BC will be perpendicular to the radius SO. If BC is perpendicular to SO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Here we can implement rule 2 in our drawing. But before that, we will join points O and Q together by a straight line. OQ is of course the radius of this circle, is equal to 1. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the next step, we will implement rule 2 in our drawing. So please click on rule 2. According to rule 2, the lengths of two tangents from a common start point to a circle are equal. In the drawing, we have a circle. This is the common start point, point P. From this common start point, point P, we have two tangents to the circle, tangent PA and tangent PB. We have tangent PA and tangent PB. And according to rule 2, this one, rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. If we focus on this common start point, point B, from the common start point, point B, we have two tangents to this circle, tangent BS and tangent BL. And according to rule 2, they are equal to each other. That is to say, BS equals to BL. So if we define the length of tangent BS as A, then the length of tangent BL must be also equal to A because they are equal to each other according to rule 2. So BS equals to A, SC equals to BC minus BS. Again, SC equals to BC minus BS. So SC in total equals to BC, that is 9, minus BS, that is A. So in total, SC equals to 9 minus A units in its length. So it is 1. We focus on this common start point, point C. From this common start point, point C, we have two tangents to this circle, tangent CS and tangent CQ. And according to rule 2, they are equal to each other. That is to say, CS equals to CQ. But CS equals to 9 minus A, therefore CQ must be also equal to 9 minus A units in its length according to rule 2. What is the length of tangent AL? AL equals to AB minus LB. Again, AL in total equals to AB minus LB. So AL in total equals to AB, that is 6, minus AB, that is 8. So in total, AL equals to 6 minus A units in its length. So we focus on this common start point, point A. From this common start point, point A, we have two tangents to this circle, tangent AL and tangent AQ. According to rule 2, they are equal to each other. That is to say, AL equals to AQ, but AL equals to 6 minus 8, therefore AQ must be also equal to 6 minus 8 units in its length according to rule 2. AL equals to 6 minus 8. According to what is given as the question, AC equals to 7. So AC equals to AQ plus QC. Again, AQ plus QC equals to AC. AC equals to AQ plus QC. AQ plus QC. So AC in total equals to AQ, that is 6 minus A, plus QC, that is 9 minus A. So in total, AC equals to 6 minus A plus 9 minus A. So AC equals to 6 plus 9, that is 15. Minus A is minus 2A. So in total, we found out that AC equals to 15 minus 2A. But AC equals to 7. So we can substitute AC by 7 and get that 7 equals to 15 minus 2A. Here we read 2A from this equation to this equation, and we subtract 7 simultaneously, and we get that 2A equals to 15 minus 7 is 8. So 2A equals to 8. Here we divide this equation by 2 and we get that A equals to 8 over 2, that is 4. A equals to 4 units in its time. AS equals to 8, that is equals to 4. PL also equals to 8, that is 4. LA equals to 6 minus 8. 6 minus 8, 6 minus 4, that is 2. AQ also equals to 6 minus 8, that is 2. QC equals to 9 minus 8. 9 minus 8, 9 minus 8, 9 minus 8 is 9 minus 4, that is 5. Likewise, ST also equals to 9 minus 8, that is 5. Our task is to find out the area of this green shape. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. Repeat again. The sum of the angles in any quadrilateral is equal to 360 degrees. So, in quadrilateral QOSC, the sum of the angles must be equal to 360 degrees. So which angles we have in quadrilateral QOSC? $90 degrees plus 90 degrees is 180 degrees. This is angle theta plus this missing angle, that is actually angle SOQ. In total, the sum of those four angles must be equal to 360 degrees according to the rule that I mentioned. And again, the sum of the angles in this quadrilateral QOS equals to 360 degrees. That is to say, 180 degrees plus theta plus the missing angle SOQ. In total must be equal to 360 degrees. Here we subtract 180 degrees from this equation. Again, that theta plus the missing angle SOQ is equal to 360 degrees plus 180 degrees, it is 180 degrees. So theta plus the missing angle SOQ is equal to 180 degrees. This is the missing angle SOQ. Here we subtract theta from this equation. And finally, we get that the missing angle SOQ is equal to 180 degrees minus theta. And again, I should find out that this is the missing angle SOQ is equal to 180 degrees minus theta. But we only found out that 180 degrees minus theta equals to 139.632. So the missing S for Q is equal to 139.632 degrees in its size. We have a special formula that states that any triangle that blocks a circle, any triangle that blocks a circle, like in our drawing, the radius of any triangle that blocks a circle is equal to S times R. R is the radius of this circle that is inscribed by triangle ABC, and S is the semi-perimeter of triangle ABC. We already found out that the semi-perimeter of this triangle ABC is equal to 11 units in its length. So, okay, again on the formula, the triangle ABC, according to the new formula that I mentioned, is equal to S times R. S is the semi-perimeter, is equal to 11. R is the missing radius of this circle that is inscribed by triangle ABC. And we already found out that the triangle ABC is equal to 2 times square root of 110. And again, the triangle ABC equals, according to what we already found out, is equals to 2 times square root of 110 units in its size. So the triangle ABC equals to S times R. That's actually 2 times square root of 110 equals to R, 11 times R. Here we divide this equation by 11, and finally get that the radius of this circle that is inscribed, the radius of this circle that is inscribed by triangle ABC is equal to 2 times square root of 110 over 11. And 2 times square root of 110 over 11 is equal to 1.907. So in total we found out that the radius of this circle R is equal to 1.907 units in its length. In the next step, we will join point C and O together by a straight line. But before that, OQS is a sector. And again, OQS is a sector. What is a sector? A sector is a portion of a circle closed by 2 radii and the arc between the 2 radii. This is sector A or B, the green shape. It is a portion of this circle enclosed by 2 radii and arc AB between the 2 radii. The 2 radii AO and BO are defined as the legs of this sector. And the angle between the legs of the sector is theta. So this is the area of the sector A of B. This equals to pi r squared. It is the area of the second that contains the sector times the angle between the legs of the sector theta over 360 degrees. Repeat again. The area of the sector A of B equals to pi r squared times theta over 360 degrees. So here OQS is the sector of this circle. So in the next step, we will join points C and O together by a straight line. So joining points C and O, we created two right angles. This is the right triangle OQC and this is the right triangle OSC. Our test, we would like to find out the area of this green shape. So what is the area of the green shape? For drawing, it is very easy to see that the area of this green shape equals to the area of quadrilateral QOSC, this quadrilateral QOSC, minus the area of this sector, sector OQS. And again, it is very easy to see from the drawing that the area of this green shape in total is equal to the area of quadrilateral QOSC minus the area of sector OQC. The rounded line above OQC is the sign of a sector, it means sector OQC. What is the area of this quadrilateral? Quadrilateral OQCS. Actually, quadrilateral OQSC consists of those two triangles, and therefore the area of quadrilateral QOSC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of this right triangle OQC plus the area of this right triangle OSC. So I write it down. First we found out that the area of the big quadrilateral QOSC, so it is equal to the area of this right triangle OQC plus the area of this right triangle OSC. And again, the area of this quadrilateral OQC must be equal to the sum of the areas of those two shapes that it consists of. That is to say, the area of quadrilateral OQC must be equal in total to the area of the first shape, that is right triangle OQC, plus the area of the second shape, that is right triangle OSC. Minus the area of this sector, sector QOS. This is sector QOS. What is the area of sector QOS? Actually, according to the formula that I presented to you, the area of sector OQS must be equal to the area of the circle that contains the sector, that is actually pi r squared, r is the radius, times the angle between the legs of this sector, that is actually 139.632 degrees, over 360 degrees. But again, there this circle OQS. In total, it is equal to pi r squared, that is the area of the circle that contains the circle, times the angle between the legs of the circle, that is equal to 129.632 degrees over 360 degrees. So the area of the green shape, in total it is equal to the area of the right triangle OQC. What is the area of this right triangle OQC? Actually, the triangle is equal to the base of the triangle times the height over 2. The base OQ is R times the height QC is 5. Yeah, the height QC is 5. Divided by 2. So in total, we should know that the area of the right triangle OQC is equal to 5r over 2 square units in size plus the area of this right triangle OSC. The area of this right triangle OSC must be equal to the base OS, that is R, times the height SC, that is 5. So in total, 5 divided by 2. So in total, the area of this triangle OSC is equal to 5R over 2. Minus the area of this sector OQS. Actually found out that the area of sector OQS equals to pi r squared times 139.632 degrees over 360 degrees. We already found out that R equals to 1.907 units in its name. So it is pi and R is 1.907 and therefore R squared is 1.907 squared times 139.632 degrees over 360 degrees. So the area of the green shape in total is equal to the value of this big expression. So here we have 5r over 2 plus 5 over 2 is 5r minus the value of this big expression. Pi times 907 squared times 139.632 degrees over 360 degrees. In total, the value of this big expression is equal to 4.387 square units in size, that is the area of sector OQS. So in total, we should know that the area of the green shape it is equal to 5r minus 4.387 degrees. R is 1.907 and therefore 5r is 5 times 1.07 is actually 9.345. Is actually the sum of the areas of the two right triangles minus the area of sector OQS, that is equal to 4.387 squared in its size. So the area of the green shape in total equals to 9.535 minus 4.387 is equal to 5.148 squared in its size. So if you found out that the area that we are looking for in this question, that is the area of the green shape, in total it is equal to 5.148 148 square in size. So we finish with the first question. In the next step, I will present you the second question. And we solve the second question by using 3 different methods. Our task in the second question is to find out the area of this square ABCD. And again, our task is to find out the area of this big square ABCD. So in the drawing, first square ABCD, this is diagonal DB. This is angle BDP is equal to 30 degrees in size. This is angle PBC. This is also equals to 30 degrees in size. BP equals to 5 units in its length. And again, BP equals to 5 units in its length. And again, our task is to find out the area of this big square ABCD. So first of all, we know that the diagonals of a square bisect the angles of the square. Again, the diagonals of a square bisect the angles of the square. Diagonal DB bisect angle ADC. The first half, this is the first half, this is actually 45 degrees in size. This is the second half. It is also equals to 45 degrees in size. So the second half equals to, this is the second half, this equals to 45 degrees in size. But this again equals to 30 degrees, therefore this angle must be equal to 15 degrees in size. So 15 plus 30 is 45 degrees. That is the second half of angle ADC. Likewise, diagonal DB bisect angle ABC. So this is the first half, this equals to 45 degrees in size. So this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in size in order to complete the first half to 45 degrees. 30 degrees plus 15 degrees is 45 degrees. This is the second half of angle ABC, that equals to 45 degrees in size. In the next step, we will do a construction. That is to say, from this point, from the vertex C of the square ABCD, we will draw angle bisector of angle DCB. Again, from point C, we draw angle bisector of this angle DCB. So angle bisector DCB bisect angle DCB, this is 90 degrees. The first half is 45 degrees. The second half is also 45 degrees. Angle bisector bisect angle DCB into two halves. Each half must be equal to 45 degrees. In the next step, we'll extend side DP by straight line until it will touch the angle bisector. When we find the touching point of the extended line 7 dp with this angle bisector, this point is point Q. So actually, by doing this construction created here, triangle DQB. This is triangle DQC. Triangle DQC, this angle equals to 15 degrees. This angle equals to 45 degrees. 15 degrees plus 45 degrees is 60 degrees. So the missing angle must be equal to 120 degrees in its size, according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. 180 degrees plus 60 degrees is 120 degrees plus 60 degrees is 180 degrees. So this missing angle equals to 120 degrees in its size. In the next step, we'll join points Q and B together by straight line. By joining points Q and B, we create triangle BQC. In the next step, we prove that those two right triangles can go into each other according to side against side rule. That is to say, right triangle DQC can go into this triangle CBQ according to side against side rule. So we have to prove that this is triangle DQC. We have to prove that this triangle DQC can go to this triangle BQC. So, why those two triangles can go into each other? First of all, BC equals to DC, because ABCD is a square, and we know that all the sides of any square are equal to each other. So side BC of triangle BDC is equal to this side DC of triangle DQC. It again. Side BC of triangle BQC is equal to side DC side BC of triangle DQC is equal to side DC. Side BC of triangle BQC is equal to side DC of triangle DQC. those two angles are both equal to 45 degrees and therefore they are equal to each other. So actually this is angle BCQ. So angle BQC is equal to this angle. There's actually angle DCQ. Of triangle DQC. And again, I'm sure some of that angle BCQ of triangle BQC is equal to angle DCQ of triangle DQC. They are both equal to 45 degrees and therefore they are equal to each other. And finally, side QC is a common side. Side QC is a common side that belongs to both triangles. So we can write down that QC equals to itself as a common side that belongs to both triangles. QC is a common side that belongs to both triangles, so QC equals to itself. It's a common side. So if you found out that those two sides and the angle that is included between those two sides, this triangle BQC are corresponding equal to those two sides and the angle that is included between those two sides, the triangle DQC. And therefore those two triangles can go into each other according to side angle side rule. We have two sides and the angle that is included between them in this triangle BQC are corresponding equal to those two sides and the angle that is included between those two sides in triangle DQC. And therefore those two triangles can go into each other according to side angle side rule. So maintenant, je vais voir that triangle BQC can went this is the same can went to triangle BQC forming so side angle side rule. And from the fact that those two triangles can go into each other, we derive that those two angles are equal to each other according to the rule that corresponding angles that can go into triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other according to the rule that I mentioned. So this is angle QDC in triangle DQC. Is equals to this angle, the angle QBC. Triangle BQC. This angle equals to 15 degrees in its size. So from the fact that those two triangles can go into each other, we derive that angle QDC equals to angle QBC. But angle QDC equals to 15 degrees in its size. Equals to 15. And for this equation, 15 equals to angle QDC equals to angle QBC. We derive that angle QBC also equal to 15 degrees in its size. This is again QBC. It's equals to 15 degrees in its size. In the next step, we'll focus on this tile DBP. Actually, we will implement right in this tile DBP. So I'll copy tile DBP in the new page and we'll implement all 8 in this tile DBP. All 8 is about an external angle. This is triangle DBP, is according to the original drawing. Those three angles are defined as interangles. This is again BPQ. It is defined as an extrangle because it is located outside triangle BDP. So I please click on rule 8 and implement rule 8 in our drawing. According to rule 8, the extrangle of a triangle is equal to the sum of the two interangles that are not adjacent to it. In the drawing we have triangle ABC. Those triangles alpha, beta and gamma are defined as interangles of triangle ABC. This is angle E. Angle ECB is equal to E degrees in size. Angle E is the extrangle of triangle ABC. According to this rule 8, the size of this extrangle E is equal to the sum of the two interangles that are not adjacent to it. This is angle gamma, this is definitely adjacent to angle E. The two other angles that are not adjacent to angle E, are those two angles. So, the size of angle E is equal to the sum of the two angles that are not adjacent to it. That is to say it is equal to alpha plus beta, because they are not adjacent to angle E. So, E equals to alpha plus beta. And implement rule 8 in our drawing. This is the extrangle BPQ. What is the size of extrangle BPQ? According to rule 8, it is equal to the sum of the two interangles that are not adjacent to it. Those are the two interangles that are not adjacent to it. Therefore, the extrangle BPQ must be equal to 15 plus 30, it is 45 degrees. Again, this is again BPQ. The extrangle BPQ is equal to 30 degrees plus 15 degrees according to rule 8. So the missing angle BPQ is equal to 30 degrees plus 15 degrees is 45 degrees. So actually, this is the missing angle BPQ. This is the missing angle BQP. BPQ, this is the missing angle BPQ. This is equal to 45 degrees in size, according to rule 8. In the next step, we prove that those two triangles can go into each other according to side angle rule. Prove that this is the right angle PQC. This is can go into this angle BPQ according to angle side angle rule. So we prove that those two right angles can go into each other. So triangle BCQ, this triangle can went to this side BQP according to angle side angle rule. So why those two triangles can go into each other? First of all, those two angles are both equal to 45 degrees, therefore they are equal to each other. So here this angle BCQ, the triangle BQC is equal to this angle, therefore angle BPQ. This triangle BQP. And again, I should also that angle BCQ, triangle BQC is equal to angle BPQ, and triangle BQP. They are both equal to 45 degrees, and therefore they are equal to each other. This is side QB. It is a common side that belongs to both triangles. So you can write down that QB equals to itself. It's a common side that belongs to both triangles. And again, QB equals to itself is a common side that belongs to both triangles. What is the size of this angle? We know that in total, diagonal DB bisect angle ABC into two halves. Each half must be equal to 45 degrees in its size. The first half is 45 degrees, This is the second half. It must be also equal to 45 degrees in its size. 15 degrees plus 15 degrees is 30 degrees, and therefore this further side must be equal to 15 degrees in its size in order to complete the second half to 45 degrees. 15 times 3 is 45 degrees. So this is the missing side is equal to the missing angle is equal to 15 degrees in its size. So actually, those two angles are both equal to 15 degrees and therefore they are equal to each other. So actually this angle QBC is angle QBC is equal to this angle. This is actually angle QBP. It's angle BPQ. Again, if you know that angle QBC, angle BCQ equal to angle QBP, angle BQP, they are both equal to 15 degrees and therefore they are equal to each other. So I actually found out that before that we have this is triangle BQC. It's triangle BQC. This angle goes to 15 degrees. This angle goes to 45 degrees. 45 degrees plus 15 degrees is 60 degrees, and therefore this third angle must be equal to 120 degrees in its size, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. We know that the sum of the angles around any point is equal to 360 degrees. Okay, again, the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point Q must be equal to 360 degrees. 120 degrees plus 120 degrees is 240 degrees, and therefore this further angle must be equal to 120 degrees in its size in order to complete the sum of the angles around point Q to 360 degrees. This missing angle must be equal to 120 degrees in its size. So we should found out that those two angles and the side that is included between those two angles, side QB, and triangle BQC are possibly equal to those two angles and the side that is included between those two angles, that is also side BQ, and triangle PQB. And therefore, those two triangles can run to each other according to angle side angle rule. We have those two angles and the side is included between those two angles in triangle QBC are corresponding equal to those two angles, and the side that is included between those two angles in triangle PQB. And therefore, those two triangles can point to each other according to angle side angle rule. So if you found out that triangle BCQ can point to triangle PQP, according to angle side angle rule. And from the fact those two triangles can go into each other, we derive that those two sides are equal to each other. Why those two sides are equal to each other? Those two sides are equal to each other according to the rule that says that corresponding sides in congruent triangles are equal to each other. those two triangles can go into each other, therefore those two corresponding sides must be also equal to each other on their lengths. That is to say, BC equals to PB. BC equals to PB. But it is given us the question that PB equals to 5. So if you write here that PB equals to 5, and for this equation, BC equals to PB equals to 5. We will derive that BC also equals to 5. BC equals to 5 units in its length. This is side BC of square ABCD equals to 5 units in its length. So our task is to find out the area of this big square ABCD. We know that the area of any square equals to the length of one side of the square squared. And the area of any square equals to the length of one side squared. So the area of the big square ABCD must be equal to the length of BC squared. But BC is 5, so BC squared is 5 squared. 5 squared is 25. So in total, we should know that the area of this square ABCD is equal to 25 square units in its size. So we finish with the first method. The next step, I present to you how to find out the area of this big square ABCD according to the second method. So, in the second method, we know that the diagonals of a square bisect the angles of a square. Diagonal DB bisect angle ABC. The first half, this is the first half, this is 45 degrees. This is the second half, this is also 45 degrees. But this angle equals to 30 degrees, therefore this missing angle must be equal to 15 degrees in its size. 15 plus 30 is 45 degrees, that is the size of the second half. So this is triangle BDP. This is triangle BDP. This angle equals to 15 degrees. This angle equals to 30 degrees. 15 degrees plus 30 degrees is 45 degrees. And therefore, this surface area must be equal to 135 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So this surface area must be equal to 135 degrees in its size. Diagonal BD bisect angle ADC into two halves, so the first half is 45 degrees. This is the second half, is also 45 degrees, and therefore this missing angle must be equal to 15 degrees in size, because 1 plus 15 plus 30 degrees is 45 degrees, that is the size of this second half. If I can see dA. In the next step, we will do a construction. That is to say, from the vertex, we will draw a circle around this square ABCD. Again, we will draw a circle around this square ABCD. Point A will be the center of the circle that we will draw, and the radius of the circle will be equal to the side length of square ABCD. So the radius of the circle is equal to AB. We define AB as x. AD is also the radius of the circle is equal to x, according to our definition. Okay, again, we draw a circle around this square ABCD in such a way that point A will be the center of the circle, and the radius of the circle that we draw will be the side length of square ABCD. AB equals to AC equals to x. This is the radius of the circle that we will draw. So actually, this is the circle that we draw around square ABCD. Point A is the vertex. Vertex A is the center of this circle, as you can see. AB is the radius of the circle that equals to x. AD is also the radius of the circle that is equal to x. Actually, if you draw a circle in such a way that the center of the circle will be at point A, then the circle and ABCD is a square, and the radius of the circle is one side of square ABCD equals to x, then the circle must pass from point B and D. Actually, it is very easy to prove that the circle must pass from point B and D. I will not prove it, but it is very easy to prove that whenever you draw a circle around the square, that the center is at vertex A and the radius of the circle is equal to the side length of the square, then it is very easy to prove that the circle must pass from point B and D. I will not prove it, but it's very easy to prove it. So here, this is the circle that passes from point B and D, the two vertices of square ABCD. This angle is a right angle. We know that the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point A is equal to 360 degrees. So this angle equals to 90 degrees, and therefore this missing angle must be equal to 270 degrees, because 270 degrees plus 90 degrees is equal to 360 degrees. This is the sum of the angles around point A. Okay. We already found out that angle BPD, this angle BPD, is equal to 135 degrees in size. This angle BPD is equal to 135 degrees in size. Here we can implement rule 13. I can click on rule 13. According to rule 13, the central angle is twice as large as the peripheral angle subtended on the same chord. In the drawing, we have a circle. This is peripheral angle ACB that's subtended on chord AB, and this equals to 10 degrees in its size. So the central angle AOB that's subtended on the same chord AB must be twice as large as peripheral angle ACB, because they are both subset on the same chord called AB. Peripheral angle ACB equals to theta, and therefore center angle EOB must be equal to 2 theta. So you can actually implement rule 13 in our drawing. Why? Because we have center angle BAD. This is the big center angle BAD. This is equal to 270 degrees in its size, and subset of chord BD. Again, center angle BAD, subset of chord BD, and it equals to 270 degrees in its size. This is again DBP. This is also subset on chord DB, and is equals to 135 degrees in its size. And because of the fact that angle DBP obeys to rule 13, we derive that angle DBP must be a peripheral angle. Why it obeys to rule 13? Because of the fact that center angle DAB is equal to 270 degrees in its side, and it's subset of chord DB. Angle DPP equals to 270 degrees over 2, that is 135 degrees. So angle DBP is half of center angle BAD, and they are both subset on the same chord called BD. And therefore it obeys to rule 13, because center angle peripheral angle, if DBP is a peripheral angle, and it is equal to half of the center angle BAD. 270 degrees over 2 is 135 degrees. And because of the fact that angle DBP obeys to rule 13, we must conclude that angle DBP is a peripheral angle. And because of the fact that angle DPB is a peripheral angle, it means that the vertex P must lie on the circle. Again, because of the fact that peripheral angle DPP obeys to rule 13, because of the fact that angle DPP obeys to rule 13, angle DPP is a peripheral angle, and therefore point P lies on the circle itself. Any peripheral angle have three vertices, now both lie on the circle. All the three vertices, so any peripheral angle lie on the circle. So point D lie on the circle, point B lie on the circle, and point P must lie on the circle itself. So we found out that point P lie on this circle. Okay. So in the next step, we'll join points A and P together by a straight line. So by joining points A and P, we actually created right triangle APB. This is the right triangle APB that we created by joining points A and P together by a straight line. Point A is the center of the circle, point P is the point of the circle itself, therefore AP is the radius of the circle, is equal to x according to our definition. So this is angle ABP is equal to 45 degrees plus 15 degrees is 60 degrees. So in the next step I'll copy this triangle ABP in a new page and we analyze this triangle ABP. Then again, ABP is equals to 45 degrees plus 15 degrees is 6 degrees. And again, this is again ABP is equals to 16 degrees in size. So actually this is triangle ABP that I formed from the original drawing. In triangle ABP, this angle equals to 60 degrees. We have the rule that says that in front of equal sides in the triangle there are equal angles. So those two sides are both equal to x and therefore they are equal to each other. So in front of those two equal sides, we have those two angles that must be also equal to each other in the length. But this angle equals to 60 degrees and therefore this missing angle must be also equal to each other according to 60 degrees, according to the rule that I mentioned. In triangle ABP, 60 degrees plus 60 degrees is 120 degrees. Therefore, this missing angle must be equal to 60 degrees in its size, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So, in quadrangle ABP, we have three angles that are both equal to 60 degrees, and therefore, triangle ABP is an equilateral triangle. Once we know that all the sides of any equilateral triangle are equal to each other. AB equals to VP equals to AP. So AB equals to BP. AB equals to X. Okay, BP equals to 5 according to what is given as the question. BP equals to 5. And for this equation, AB equals to BP equals to 5. We know that AB equals to 5 units in its length. This is side AB. Is equal to 5 units in its length. Our task is to find out the area of the square ABCD. The area of any square equals to the length of one side squared. So the area of square ABCD must be equal to the length of one side, that is AB squared. AB is 5, therefore AB squared is 5 squared, that is 25. So now we should know that the area of this square ABCD is equal to 25 square units in its size. Okay, here's the second method. In the next step, I'm going to you how to find out the area of this square ABCD according to the third method. In the third method, we define side AB of this square ABCD is X. Therefore, AD must be also equal to X. Diagonal BD of square BCD bisect the angles of square BCD. Diagonal BD bisect angle ADC. The first half is 45 degrees. The second half is also 45 degrees. So the second half is 30 degrees plus 15 degrees. That is 45 degrees. Diagonal DB bisect angle ABC. The first half is 45 degrees, and the second half is also 45 degrees. But this angle equals to 13 degrees, and therefore this angle must be equal to 15 degrees, because 15 degrees plus 30 degrees is 45 degrees. That is the size of the second half of angle ABC. So in this triangle BDP, 30 degrees, 30 degrees plus 15 degrees is 45 degrees, and all this further area must be equal to 135 degrees in its size, according to draw that said that the sum of the angles in the triangle is equal to 180 degrees. This is of course a right angle. So I can implement the Pythagoras theorem on this triangle, the big triangle ABD. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ABD, x squared plus x squared equals to bd squared. So again, x squared plus x squared equals to bd squared. So I write it down. The big right triangle ABD, according to the Pythagoras theorem, here by PT is the proportion for Pythagoras theorem. X squared plus x squared equals to bd squared. X squared plus x squared is 2x squared, so 2x squared equals to bd squared. Here we take a root out of this equation and find out that the missing hypotenuse BD is equal to the square root of 2, and the square root of x squared is x. So today we found out that the missing hypotenuse BD is equal to the square root of 2 times x units in its length. This is missing hypotenuse BD is equal to the square root of 2 times x units in its length. So we focus on triangle BDP. This is the big triangle BDP. So here we can implement the law of sines in this big triangle BDP. Repeat quickly on the law of sines. The law of sines is true in any triangle. This is triangle ABC that could be any triangle. Side AB, side AC of triangle ABC equals to B units in its length, side AB equals to C units in its length, side BC equals to A units in its length. So in this triangle ABC that could be any triangle, the following equation is true. A over sinus A equals to B over sinus B equals to C over sinus C. Actually, capital A is the size of angle BAC. Capital C is the size of angle ACB, and capital B is the size of this angle ABC. But again, according to the law of sines, the following equation is true, that A over sinus A equals to B over sinus B equals to C over sinus C. So I can actually implement the law of sines. In this big triangle, triangle BDP. the midterm BDP according to the law of science. Square root of 2 times x over sinus 135 degrees square root of 2 times x over sinus 45 degrees is equal to 5 over sinus 30 degrees. Again, according to the law of science, this time dBp, the following equation is 2. Square root of 2 times x over sinus 135 degrees equals to 5 over sinus 30 degrees. So it is square root of 2 times x over sinus 135 degrees. Sinus 135 degrees is equal to the square root of 2 times 2. And it equals to 5 over sinus 30 degrees. Sinus 30 degrees is 1 half. So we should find out that square root of 2 times x over square root of 2 over 2 equals to 5 over 1 half. 5 over 1 half is 10. And it equals to square root of 2 over square root of 2 over 2. Here we move 2 to the numerator and square root of 2 to the denominator and get that this expression in total equals to the square root of 2 times x over square root of 2 times 2. So in total, this expression equals to the square root of 2 times x times 2 over square root of 2. We have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled. So in the left only is 2x. So total 10 equals to 2x. Here we divide this equation by 2 and finally get that x equals to 10 over 2 is 5. X is the length of one side of square ABCD. X equals to AB. What else is to find out? They have this square ABCD. They have square ABCD. Equal to x squared. X is 5, so x squared is 5 squared, that is 25. So we should find out that there of this square is equal to 25 squared in size, So in both, all the three methods, we arrived to the same result. The area of this square ABCD equals to 25 squares in its size. So in the next step, I'll start the lecture. Start with the first method, of course. Actually, we'll start with the first question and then we'll repeat on the three methods of the second question. Our task, the first question is to find out the area of this green shape. So in the drawing, a circle that is described by triangle ABC. Again, triangle ABC blocks this circle. In addition, we know that AB equals to 6, AC equals to 7, BC equals to 9. Again, our task is to find out the area of this green shape. First of all, we define the size of this angle ACB as theta. Implement the law of cosines in this triangle, triangle ABC. Actually, according to the law of cosines, the law of cosines is for an triangle. This is triangle ABC that could be any triangle. AB equals to A, AC equals to B, BC equals to C, angle BAC equals to theta. In this triangle ABC that could be any triangle, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. We can implement the law of cosines in our drawing. According to the law of cosines, we get that cosine theta equals to 7 squared plus 9 squared minus 6 squared over 2 times 7 times 9. And again, according to the law of cosines, we get the cosine theta equals to 7 squared plus 9 squared minus 6 squared over 2 times 7 times 9. 7 squared is 49, plus 9 squared is 81, plus 6 squared is 36. 7 times 9 is 63, 63 times 2 is 126. 49 plus 81 is 130, 130 minus 36 is 96. So to that we should know that cosine theta equals to 96 over 126. 96 over 126 is 0.7169. We would like to find out the value of angle theta itself. In order to find out the value of angle theta, we operate the opposite function of cosine, that is r cosine, on the result of cosine theta, that is 96 over 126. And this way we get the value of theta itself. So r cosine on the result, that is 0.7169, equals to angle theta itself. R cosine of 0.7169 is 40.368 degrees. So theta equals to 40.368 degrees in its size. And therefore 180 degrees minus theta was equal to 180 degrees minus 40.368 degrees, that is 139.632 degrees. Again, in total we have found that 180 degrees minus theta equals to 139.632 degrees. we have a special formula for the affine triangle. The affine triangle equals to the square root of s times s minus a times s minus b times s minus c. S is the semi-perimeter of triangle ABC. The semi-perimeter of any triangle equals to the perimeter over 2. The perimeter is a plus b plus c over 2, or 6 plus 7 plus 9 over 2. Again, the semi-perimeter is 6 plus 7 plus 9 over 2. So the semi-perimeter of triangle ABC equals to the sum of its side terms, that is 6 plus 7 plus 9 over 2. 6 plus 7 is 13, and 13 plus 9 is 22. 22 over 2 is 11. So in total, if you want that the semi-perimeter of triangle ABC equals to 11 units in its length. A is 6, B is 7, C is 9. So the area of triangle ABC equals to the square root of S is 11, S minus A is 11 minus 6, that is 5, S minus B is 11 minus 6, that is 4, times S minus C. S minus C is 11 minus 9, that is 2. So in total, if you want to know that the area of triangle ABC equals to the square root of 11 times 5 times 4 over 2. The square root of 4 is 2, so put the you take 4 out of this root and get that 2 times the square root of 11 times 5 times 2 equals to the area of triangle ABC. 11 times 5 is 55, 55 times 2 is 110. So in total, we should know that the area of triangle ABC equals to 2 times square root of 120, 2 times square root of 110 square units in its size. The semi-perimeter of triangle ABC equals to 11 units in its length. So, in the next step, we define the center of this area. This point is point O. We define the point of tendency of tangent BC with this area. This point is point S. We define the point of tendency of tangent AB with this area. This point is point L. We define the point of tendency of tangent AC with this area. This point is point Q. We join points O and S together by straight line. OS is the radius of this area that we define as R. The radius of S is 1 to point S, that is the point of tendency of tangent BC with this area. And now, your velocity is 1 to the point of tendency, then tangent BC will be perpendicular to the SO. If this is perpendicular to SO, and this area equals to 90 degrees, and this area also equals to 90 degrees, according to 1. We join points O and Q together by straight line. OQ is the radius of this area that is equals to 1, and according to 1, this area equals to 90 degrees, and this area also equals to 90 degrees. When doing this construction, we get the quadrangle SOQC. We know that the sum of the areas in any quadrangle is equal to 360 degrees. Therefore, the sum of the areas in quadrangle OQSC must be equal to 360 degrees. Which angles we have in quadrangle OQSC? We have 90 degrees plus 90 degrees is 180 degrees, plus theta plus the area SOQ total must be equal to 360 degrees according to the rule that I mentioned. So, in quadrangle QOSC, the sum of the areas must be equal to 360 degrees. That is to say, 180 degrees plus theta plus the area SOQ total must be equal to 360 degrees. Here we subtracted 180 degrees from this equation, and finally found out that theta plus the area SOQ equals to 360 degrees minus 180 degrees is 180 degrees. So theta plus the area SOQ must be equal to 180 degrees. Here we subtracted theta from the equation and found out that the area SOQ equals to 180 degrees minus theta. This is the area SOQ equals to 180 degrees minus theta. But we only found out that the 180 degrees minus theta equals to 139.6 feet 2 degrees. So 180 degrees on theta equals to 139.632 degrees. In the next step, implemented rule 2 in our drawing. According to rule 2, the lengths of two tangents from a common start point to a circle are equal. So, if we focus on this point, on this common start point, point B, for this common start point, point B, we have two tangents. So this is like a tangent BS and tangent BL. And according to rule 2, they are equal to each other. That is to say, BS equals to BL. We define BS as A. Define the left side BSSA, therefore BL must be also equal to A because they are equal to each other according to rule 2. So SC must be equal to BC minus BS. So SC equals to BC, that is 9, minus BS, that is A. So in total, SC equals to 9 minus A, and it's left. From the common start point C, we have two tangents to the second, tangent CS and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BS equals to BQ. But BS equals to 9 minus A, therefore BQ must be also equal to 9 minus A, because they are equal to each other according to rule 2. The next step, so CQ equals to 9 minus A. Here we have we focus on this common start point, point A. From this common start point, point A. But before that, what is the length of LA? LA equals to BA to the 6 minus BL to the 8. So total LA equals to 6 minus A. The next step, we focus on this common start point, point A. From this common start point, point A, we have two tangents to the second, tangent AL and tangent AQ. So according to rule 2, they are equal to each other. That is to say, AN equals to AQ. But AL is 6 minus A, therefore AQ must be also equal to 6 minus A in its length. AC equals to 7, according to what is given as the question. But AC consists of two line segments, AQ plus QC. So AC in total equals to AQ plus QC. AC equals to AQ plus QC. So AC equals to AQ, that is 6 minus A, plus QC, that is 9 minus A. So in total, AC equals to 6 minus A plus 9 minus A. So AC equals to 6 plus 9 is 15, minus A minus A is minus 2A. So AC in total equals to 15 minus 2A. AC is 7, so we substitute AC by 7. So if we found out that 7 equals to 15 minus 2A. Here we added 2A, and also subtract the 7 from this equation simultaneously. And finally found out that 2A equals to 8. Here we divided this equation by 2, and finally found out that A equals to 4. A equals to 4. 6 minus A is 6 minus 4, that is 2. 6 minus A is 2. QC equals to 9 minus A. 9 minus A is 9 minus 4, that is 5. So 9 minus, CS equals to 9 minus A, that is 5. So in the next step, we join points O and C together by a straight line. We have a special formula for a triangle that blocks a circle. Again, we have a special formula for a triangle that blocks a circle. This is a triangle ABC that blocks this circle. According to the special formula, any triangle that blocks a circle is equal to the semi-perimeter of the triangle. In our case, it is 11 times the radius of the circle that is inscribed by triangle ABC. And of this triangle ABC is equal to the semi-perimeter of this triangle, that is 11, times the radius of the circle R that is inscribed by triangle ABC. So the triangle ABC equals to the semi-perimeter times the radius of the circle that is inscribed by triangle ABC. So the area triangle we see is 2 times root of 10 according to what we already found out. S is 11, R is the missing variable. So if you want the 2 times root of 10 equals to 11 times R. Here we divided the equation by 11. If I found out that the radius R of this circle is equals to 2 times root of 110 over 11. 2 times root of 10 over 11 is 9.07 units. So the radius of this circle R equals to 9.07 units in its length. In the next step, explain to you what is a sector. A sector is a portion of a circle. This is a sector OQS. It is a portion of a circle enclosed by two radii and the arc US between them. This is sector AOB. It is enclosed by two radii and arc AB between those two radii. The two radii we find as the legs of the sector. So the angle between the legs of the sector is theta. The area of the sector AOB will be equal to pi r squared, that is the area of the circle that contains the sector, times angle theta, that is the angle between the legs of the sector, over 360 degrees. Again, the area of the sector will be equal to pi r squared times theta over 360 degrees. Our task is to find out the area of these benches. This is quadrangle QOSC. For the moment, it is very easy to see that the area of this ring shape in total equals to the area of quadrangle QOSC plus the area of sector OQS. And again, the area of the green shape in total equals to the area of the big quadrangle QOSC plus the area of sector OQS. The rounded line above OQS is the sign for a sector. This is sector OQS. What is the area of the big quadrangle QOSC? Actually, the area of quadrangle QOSC must be equal to the sum of the areas of the two shapes that it consists of. Quadrangle QOSC consists of those two right angles, and therefore the area of quadrangle QOSC must be equal to the sum of the areas of those two right angles. So the quadrangle QOC must be equal to the area of the first right angle OQC plus the area of the second right angle OSC. Then the area of the big quadrangle QOC must be equal to the area of the first right angle OQC plus the area of the second right angle OSC. Minus the area of sector SQ. OSQ. What is the area of this sector? OQS. According to the formula that I presented to you, the area of sector OQS must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the circle, that is under 39.632 degrees or 360 degrees. And again, the area of the sector OQS in total equals to the area of the circle that contains the circle, that is pi r squared, times the angle between the legs of the circle, that is under 39.632 degrees over 360 degrees. What is the area of this line OQC? The area of the OQC equals to the base OQ times the height QC over 2. The base OQ is R and QC is 5, so it is 5 times R over 2. The area of the right angle OQC is 5 over 2 plus the area of this right angle OSC. The area of this right angle OSC equals to the base OS, that is R, times the height SC, that is 5, divided by 2. And therefore, the area of the right angle OSC also equals to 5 over 2 minus the area of sector OSQ, that is equal to this expression. We already found out that R equals to 1.907. Therefore, r squared is 1.907 squared. So total the obstacle r squared equals to pi times 1.907 squared times 139.632 degrees over 360 degrees. 5r over 2 plus 5 over 2 is 5r. In total, the value of this expression is equal to 4.387 seconds in size. This is the obstacle or QS. So in total, the obligation equals to 5r minus 3.87. R is 1.907, and therefore 5r is 5.1907, that is 9.535 minus 3.38 minus 4.387. 9.535 minus 9.535 minus 4.387 equals to 5.148 seconds in size. Total, if you found out that the area of this relationship, that is the area that you are working for this question, is equals to 5.148 seconds in size. So we finished with the first question. In the next step, I'll repeat on the solution of the second question. We solved the second question in 3 different methods. So we'll start with the first method. Our task in the second question is to find out the area of this big square ABCD. In the drawing, we have diagonal DB. This is diagonal DB. This is again BDP equals to 30 degrees in size. This is again BBC, this also equals to 30 degrees in size. This is line 7 BP. This is line 7 BP, this equals to 5 units in its length. Again, our task is to find out the area of the square ABCD. So first of all, we know that the diagonals of a square bisect the angle of the square. Again, the diagonals of a square bisect the angles of the square. So diagonal DB bisects the angle ABC. Angle ABC is, total is 90 degrees, and therefore the first half has to be equal to 45 degrees, and the second half, this is the second half, is equal to 45 degrees. But this angle equals to 30 degrees, and therefore this means has to be equal to 15 degrees inside, because 15 plus 30 is 45 degrees. That is the size of the second half of angle ABC. So diagonal BD bisect angle ADC. So the first half is 45 degrees, the second half is also 45 degrees. But this angle is 30 degrees, and therefore this means angle must be equal to 15 degrees in size. So it's 15 plus 30 plus 15 degrees is 45 degrees. This is the size of this second half of angle ADC. In the next step, we did the construction, that is to say, from point C, we draw angle bisector of angle DCB. So CQ is angle bisector of angle DCB, and therefore the first half is 45 degrees and the second half is 45 degrees. In the next step, we extended line 7DP by side line until it touches the angle bisector. We define the touching point of the extended side DP with this angle bisector. This point is point Q. By doing this construction, we created triangle DQC. Triangle DQC This angle equals to 15 degrees, this angle equals to 45 degrees. 15 plus 45 is 60 degrees. Therefore, this fifth angle must be equal to 120 degrees inside, according to the rule that says that the sum of the angles in any triangle is equal to 120 degrees. Okay, so the next step is prove that those two right angles can go into each other according to side angle side law. So again, we prove that triangle DQC can go into this triangle BQC according to side angle side law. So when those two triangles can go into each other. First of all, side DC equals to side BC, they are both the sides of a square that are equal to each other. In addition, those two angles are both equal to 45 degrees and therefore they are equal to each other. And finally, QC is a common side that belongs to both triangles. So you can write down that QC equals to itself is a common side that belongs to both triangles. So if you prove that those two sides and the angle that is included between those two sides of the triangle QC are correspondingly equal to those two sides and the angle that is included between those two sides and triangle CQD. Therefore, those two triangles can go into each other according to side angle side laws. Triangle DQC can go into triangle BQC according to side angle side law. And for the fact that those two triangles can go into each other, regard those two angles must be also equal to each other and their sizes. According to the rule, it says that the corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be equal to each other and their sizes. But this angle equals to 15 degrees in size. Therefore, this fifth angle must be also equal to 15 degrees in size. So, in the next step, we prove that those two triangles can go into each other according to angle side angle rule. So when those two triangles can go into each other, but before that, we forbid triangle BDP, this triangle BDP in Euclid is implemented rule 8 in this triangle BDP. This is triangle BDP that is according to the original drawing. This is the external angle BPQ, actually according to 8. An external angle of a triangle is equal to the sum of the two angles that are not adjacent to it. That is to say, angle BPQ, the external angle BPQ equals to 15 degrees plus 30 degrees, that is 45 degrees. The external angle BPQ equals to 45 degrees in size. Okay, this is the external angle BPQ, that is equals to 45 degrees in size according to rule 8. What is the size of angle PBQ? The first half of angle ABC is 45 degrees. The second half of angle ABC equals to 45 degrees. So this angle total equals to 45 degrees. So 15 degrees plus 15 degrees plus the missing angle total must be equal to 45 degrees according to the rule that the diagonal of square bisects the angle of the square. So the second half must be equal to 45 degrees in size. This is the second half. Therefore, this fifth angle must be equal to 15 degrees in size. Why? Because 15 times 3 is 45 degrees. That is the size of this second half of angle ABC. So this angle equals to 15 degrees in size. 15 plus 45 is 60. Therefore, this further angle must be equal to 120 degrees in size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. The next step, we found that those two triangles can go into each other according to angle side angle rule. So why those two triangles can go into each other? First of all, we have those two angles, they are both equal to 15 degrees and therefore they are equal to each other. And then the BQ is the common side that belongs to both triangles. And finally, those two angles are both equal to 45 degrees and therefore they are equal to each other. So we can prove that those two angles and the side that is included between those two angles, that is side BQ and triangle BQP, are corresponding equal to those two angles and the side that is included between those two angles, that is BQ and triangle BQC. And therefore, those two triangles can go into each other according to angle side angle rule. And for the fact that those two triangles can go into each other, we will derive that BC equals to PB. BC equals to BP. Those two sides are equal to each other according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding sides must be also equal to each other in their lengths. So PC equals to BP. But according to what is given in the equation, BP equals to 5. So we can write here that BP equals to 5, and for this equation BC equals to PB equals to 5. We know that BC also equals to 5 units in its length. This is side BC that equals to 5 units in its length. Our task is to find out the square ABCD. Actually, you know that the area square equals to the length of one side squared. So thereafter, square ABCD was equal to the length of one side, that is BC squared. BC squared. BC is 5, therefore BC squared is 5 squared, that is 25. So total, we found out that the area of the square ABCD equals to 25 squares in size. We finish with the first method. In the next step, I'll fit on the solution of the second method. We found out that this angle equals to 30 degrees, this angle equals to 15 degrees, according to the rule that the diagonals of a square bisect the angles of the square. This angle equals to 45 degrees, this angle equals to 30 degrees according to what is given in the equation. Therefore, this missing angle was equal to 15 degrees in size. So, triangle DBP is a triangle DBP. This angle equals to 30 degrees. This angle equals to 15 degrees. And therefore, this third missing angle must be equal to 135 degrees in size. According to the rule that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we did a construction. But before that, we defined side AD as x, therefore side AB must be also equal to x because it is a square ABCD. In the next step, we did the construction, that is to say, we draw a circle around square ABCD in such a way that point A will be the center of the circle that we will draw. AB will be the radius. So AB is the radius that equals to x, and AB is also the radius of the circle that equals to x units in its length. This is the circle that we draw round square ABCD. So the mentioned before, we take the center of the circle. AB equals to AD, the above the order of the circle, that equals to x. So here we have, this is center angle DAB, is equals to 270 degrees in its size, according to the rule that the sum of the angles around the point is equal to 460 degrees. 90 degrees plus this missing angle, total must be equal to 460 degrees, and therefore this missing angle must be equal to 270 degrees in its size. Center angle DB equals to 270 degrees in its size. This is angle DBP, this is equal to 135 degrees in its size, according to what we already found out. Angle DBP subtend on chord DB, exactly like center angle DB. DB is also subtend on the same chord called DB. Because of the fact that the center angle subtend on the same chord as this angle, and it obeys to all angle DBP obeys to all 13. It says that the center angle is twice as large as the peripheral angle that subtend on the same chord. Center angle DB subtend on chord DB, and angle DBP subtend on the same chord DB. Therefore, the size of peripheral angle in DBP must be equal to 270 degrees over 2, that is 135 degrees. And because of the fact that angle DBP obeys to all 13, angle DBP is a peripheral angle. We know that any peripheral angle, all of its three vertices lie on the circle. Point D lie on the circle, point V lie on the circle, and therefore point P must lie on the circle. Because it is a peripheral angle, because it obeys to all 13. The next step, we join points A and P together by a straight line. We join points A and P created. First of all, point A is the center of the circle, point P is the point of the circle itself, therefore AP is the radius of the circle, is equal to x. In the next step, we copy triangle APB in a new page and analyze this triangle APB. This is triangle APB, this is a common from the original drawing. Angle ABP equals to 45 degrees plus 15 degrees is 60 degrees. This is angle ABP, this equals to 60 degrees in size. In front of those two equal sides, we have those two angles that must be also equal to each other in their sizes, but this angle equals to 60 degrees, and therefore this angle must be equal to 60 degrees in size. 60 degrees plus 60 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, triangle ABP is an equilateral triangle, and you know that all the sides of any equilateral triangle are equal to each other. So AB equals to BP, because it is an equilateral triangle. But PB is 5, according to what is given in the equation, and from this equation AB equals to BP equals to 5, and we have that AB equals to 5. So the radius of AB is 5, and we know that they are very square. Our test is find out the square ABCD. You know that they are very square equals to the length of one side squared. To say it is the length of AB squared. AB is 5, so AB squared is 5 squared, that is 25. So I should found out that the of this square ABCD is equal to 25 squared according to the second method. So I repeat on the solution of the third method. In the third method, we define side AD as x, so AB is also x. This is the right angle because ABCD is a square. Implement the Pythagoras theorem on this triangle ADB. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So x squared plus x squared equals to db squared. X squared plus x squared equals to db squared. x squared plus x squared is 2x squared plus 2 dv squared. Here we took out all of the difference and found out that d equals to the square root of 2 and times the square root of x squared. The square root of x squared is x. So in total, dv equals to the square root of 2 times x squared in its size. That one on db, let's take the angles of the square. So the first half of angle ADB is 45, the second half is also 45, but this is 30, and therefore this missing angle must become to 15 degrees inside, because the second half is 30 plus 15, that is 45. Likewise, the one on dB by second angle ABC. The first half is 45, the second half is also 45. This is the second half, that is 45. But this angle is 30, therefore this angle must equal to 15 degrees inside, because 15 plus 30 is 45, that is the second half. So at angle BDP, this angle equals to 30 degrees, this angle equals to 15 degrees, and therefore this furthest angle must be equal to 135 degrees inside, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we implemented the law of sines in this triangle BDP. So according to the law of sines, the law of sines is drawn in a triangle. This is a triangle ABC that could be any triangle. AB equals to C units in itself, AC equals to B units in itself, BC equals to A units in itself. The size of angle BC is A, the size of angle ACB is C, and the size of angle ABC is B. According to the law of sines, A over sinus A equals to B over sinus B equals to C over sinus C. And again, A over sinus A equals to B over sinus B equals to C over sinus C. So we can implement all the law of sines in our drawing. Our drawing again is according to the law of sines. The square root of 2x over 135 degrees equals to 5 over 30 degrees. Again, square root of 2 times x over 135 degrees over 135 degrees equals to 5 over square root of 5 over sinus 30 degrees. Again, square root of 2 times x over sinus 135 degrees equals to 5 over sinus 30 degrees. And again, according to the law of sines, entire dBP, square root of x, square root of 2 times x over sinus 135 degrees equals to 5 over sinus 30 degrees. Sinus 135 degrees is square root of 2 over 2. Sinus 30 degrees is 1/2. So total square root of 2 times x over square root of 2 over 2 equals to 5 over 1/2. 5 over 1/2 is 10, so this expression is equal to remove 2 to the numerator and square root of 2 to the numerator, and in total we get that 10 equals to the square root of 2 times x times 2 over square root of 2. We have square root of 2 in the numerator, square root of 2 in the numerator, so square root of 2 gets cancelled, and left only is 2x in this side of the equation. So in total, 10 equals to 2x. Here we divided the equation by 2, and we found out that x equals to 10 over 2, that is 5. So x is one side of square ABCD is equal, one side of square ABCD equals to x, so the of square ABCD equals to the log of one side squared, that is x squared. X is 5, therefore x squared is 5 squared, that is 25. So if you found out that the of this square ABCD is equal to 25 squares in its size. So in all the three methods, you have to this result that the of this square ABCD is equal to 25 squares in its size. Okay, thank you very much.